Hello everyone. In this video, I'm going to present one of my graduate projects that I did for my wireless and mobile networking class. And it was on analyzing 802.11 or Wi-Fi using NS3 simulation software. So here are the main goals of the project. The main goal was to analyze 802.11 or Wi-Fi characteristics by changing different parameters such as the number of users, implementing RTS-CTS, which I will describe in detail later on. Also, parameters like distance between nodes and their effect on the network performance. So the project tools I have used Ubuntu as my Linux machine, and also I have used the NS3.26 version of NS software. So the NS or network simulator software are a series of discrete event computer network simulators. So our instructor provided us with a template C++ code to simulate a simple two-node Wi-Fi network that we have run on this NS3 software. And we have played with that code throughout the project to change different parameters of the network, as I will be describing later on. And also I have used Wireshark to analyze the traffic network, or the .pcup files or packet capture files. So throughput is the metric that we have used to analyze the performance of network. So network throughput refers to the average data rate of successful data or message delivery over a specific communication link. In other words, throughput is the amount of data transferred over a given period of time. So if more data is transferred, we get higher throughput. And this is the equation that I've used to calculate network throughput. And the first simulation I have run, these were the parameters that I have used. So it was for two nodes, and the distance between the two nodes were 100, and we have run this simulation for a total of 20 seconds. So this is the total number of packets that we have observed from the Wireshark analyzing. And the size of the packet, this is something you have to fix in your C++ code. So using all these numbers, the throughput for the two node that I've got is about 198 kilobytes per second. So after running the two node code successfully, the first task was to increase the number of users from 2 to 3 and eventually 6. And as you can see that these are from NS3 visualization tool that we have placed all the nodes in one line. And this is something that we have also fixed in our code to place all the nodes in one single line. So we observe that as we increase the number of nodes, the throughput starts to go down. Now, this was a little anti-intuitive, I guess, because we were thinking that if we increase the number of nodes, we should be receiving more packets, so the throughput should be more. But that's actually not the case, and the reason behind that is what I'm going to describe later on. So before getting into the reason, we have to know how 802.11 works. So this is the timing diagram. So in this situation, we're considering that both A and B are sending data to C, and A and B can hear each other. They're not sending data to each other, but they can hear what the others are doing. So before starting this, we have to know that each user picks a random back-off timer, like these numbers. They pick them from a window that the network administrator has to set as a parameter of the network. And when the timer goes off, they start sending data. And there are these different pauses that wireless channel implements, SIFs and diffs. Diffs is the bigger one, and SIFs is the shorter one. I'm not going to go into detail what are SIFs and diffs, but we just need to know that there are pauses just at this point. So what's happening here is that when A's timer goes to 0, it will start sending data to C. So A is sending, C is receiving. But as soon as B senses that these two are communicating, since B can hear A, it will go into busy state. And then C is saying A that I have received your data with an ACK. And then after receiving this ACK, B's busy state is over. And then again, all the timers will resume. And since A's timer already went to 0, it's going to pick a new random backup timer here, like the number 9 here. And then B's timer goes to 0, so it gets to send data to C now. And again, A can hear it, so A goes to busy, and there is another successful transmission. So this is how Wi-Fi works. So when does the problem occur, actually? So the problem occurs if, for some reason, A and B cannot hear each other. So what will happen in this case is while A and C are sending and receiving data, B's timer is going to 0, so B is starting to send data. So what immediately will happen is that this previous data transmission will be canceled, and also B cannot send data to C as well. So everyone will go to diffs, and this total time of transmission here will be lost in the channel. So that's what a collision is, and that's why throughput goes down and the whole network performance goes down because of a lot of collision. So what is the solution in here? So the solution, one of the most promising solutions, is the implementation of request to send and clear to send packets. So how this works is that when A wants to send data and it goes to 0, it will send a request to send packet to C, and C will receive it. And then C will send a CTS or clear to send packet to all of the other users that are in range. So CTS will be received by both B and A. And since B is receiving CTS, it will immediately go into busy. And A is receiving the CTS, so it knows now it can send data. So it is a successful transmission between A and C. And B's busy state will be over once it senses that there is an ACK here. And then this is how the collision of data transmission is avoided in 802.11. So the second task, obviously, was to implement RTS-CTS in our C++ code. So RTS-CTS is what enables 802.11 to follow CSMA-CA, which is, as you probably know, as Carrier Sense Multiple Access Collision Avoidance. So this is how 802.11 can avoid collisions. So here's the result comparison. We can clearly see that with the implementation of RTS-CTS, the throughput goes down from 89 kilobytes per second to almost 164 kilobytes per second, which is a huge, huge improvement because we're avoiding all those collisions. So the third task was to increase the distance between the 3 nodes. And as you can remember, the first distance we set was around 100, and then now we're increasing it to 350. Now we observe that the throughput, or the total number of packets, is going way down when we're increasing the distance between them. Now, why is that? Is it because of propagation delay, that one packet is taking more time to reach the node? Well, actually, no. It has very little to do with propagation delay. So the actual reason behind this is the hidden node problem, which is a very well-known problem in Wi-Fi. For example, A and B are both in range of C, but as you can see, A and B are out of range of each other. So this A and B are hidden to each other in this case. So what happens when we increase the distance is that we are creating more distant nodes, and we are increasing the hidden node problem. So in this situation, what happens is that A and B, if you can remember, that if they cannot hear each other, there will be collision, and this collision cannot be detected. So hidden node problem occurs with adding more and more nodes also, and also increasing the distance between nodes. And the solution in this case also is RTS-CTS, because as you can remember, that CTS will be sent to both A and B, and A will successfully go into busy state, and in this way the collision will be avoided. So some further tasks I have did for this project is to increase the number of nodes to 10 or even 20, and see what happens to the performance of the network. And in this case, as you can see, that we're placing them in a different way here. We're placing them in a circle, not in a line like before. So these are some of the things that we had to figure out in the C++ code and how to implement them. Now let's compare the results as we keep increasing the number of nodes. Well, first of all, as you can see that without RTS, the throughput is way less than with RTS CTS. It's like this, like 39 kbps compared to 160 kbps. So this is the first difference we notice. Another thing we notice is that as we keep increasing the number of users, the throughput goes down significantly in both cases, actually. So why is that again? So again, adding more and more nodes means that we are increasing the probability of hidden nodes even more, which will create more collisions, and eventually the throughput will go down. And another thing I want to mention is that even with RTS-CTS, it is not a 100% foolproof way to avoid collisions, because as you can imagine, RTS-CTS packets can still collide. Because if in any case two users pick the same random backup timer, both of their timers will go off at the same time, and then they will send the RTS packets at the same time, and they will collide. However, the reason why RTS-CTS is such a prominent solution is because the recovery time when the two RTS packets collide is way, way less than when two data packets collide. So that is why RTS-CTS is still a very, very good solution to avoid collision and improve network performance to a great extent. So to sum up, in this project I have successfully implemented an 802.11 network using NS3 software. By changing parameters like distance and user number, I was able to grasp the effects directly by analyzing the simulation results. In addition, I got familiarized with the process of creating simulations using NS3 and how the C++ codes are implemented to vary different parameters to improve network performance. So overall, this project helped me to observe a real-life implementation of Wi-Fi networks successfully. So I had a lot of fun sharing this project with you guys, and thank you for your time.